Thanks for the introduction. Excellent pronunciation of my last name. That's not easy. So, yeah, this title is a little bit vague. I might as well call it the Golang Dex subrepository, right? But some of you might know what this means or what it entails. So another title might have been internationalization and localization in Go, but that didn't fit on one line, right? So what does this actually mean, aside from being the longest terms in our field, probably? It's really a whole bunch of stuff. I won't go into the difference of internationalization and localization. It's a little bit arbitrary. You can find definitions online on Wiki, but whatever. So it's basically anything language-specific, like searching and sorting, casing, handling bidirectional text, like basically rendering Arabic and Hebrew, but also like inserting translations of your text into your code. So how do you translate your GUI? Formatting numbers, currencies, dates in different languages, but also just how do I handle text properly? So if you look at the text repo, like these are the packages that currently exist, the ones in white. So the ones in gray are currently being under development. And so that means either they're mostly or almost functional or like not at all. They're just in a design phase. So there are a bunch of categories here. So in the middle, you see the largest one. It's text processing. So these are all packages related to, you get an input string or some text, and it gets transformed into something else. So there's other packages that deal with comparison, like searching, sorting, all that kind of stuff. Text formatting. And also a very pivotal one is language tags. It's like, how do you even tell the packages what languages do you want, right? It's less easy than you might think. So all of this is native Go. So why on earth would you do that, right? It's a pretty big task. There exists something like ICU. It's pretty much the standard, right? Like a lot of languages wrap their APIs, so their frameworks are wrappers around ICU, basically. You have it for C, Java, C++. So why did we not do this in Go? So there's multiple reasons here. So firstly, the APIs in either the C, C++, or Java ICU versions are not very Go-like, if you will. It actually turns out it's very hard to come up with a Go API and then wrap it around it. So one very peculiar thing that really required a complete rewrite is, for example, if you look at streaming, Go has readers and writers, and a lot of the ICU APIs are not really geared towards that, and even the algorithms often break down under such a scenario. Another one is performance. So all of this is native UTF-8, so sometimes it's not even converted to code points, right? You just run over the UTF-8s, UTF-8 in and out. So ICU has some pretty good UTF-8 optimizations here and there, but it's primarily designed for UTF-16. So another thing that ICU does is when it loads, or when you start an application, it's sort of optimized for the case that you pick a language where you load the data for, and then you run your application for this one language. So this is not the typical Go case, right? Like in Go, you have a server that often will serve many users, many of which will have different languages. So basically what it boils down to, you will have to load the data for all languages anyway. So if you assume that this is the norm, you can actually optimize the data structures differently, right? So it won't be as big and more efficient in this case. So another very mundane one is just the cost of bridging to C is not insignificant when you're dealing with very small amounts of work. So you sometimes have to do with text. So all of this made it better to just rewrite it in Go. So just to give a little bit of a Unicode refresher and like to tell you how Go deals with Unicode in case you forgot. So Go can change over the code points. They're called runes in Go. So in the text repo, we basically use Go strings. There's nothing different. There's no separate string object or whatever. So this has a few consequences. So firstly, we're not keeping, so you have all the same features as normal Go strings, but then we're not keeping track of normalization, whether a string is normalized or not. We also don't provide random access. So for example, in Python, they go through great lengths in always being able to get, at constant time, the nth code point from a string. So with UTF-8, that's not possible by default, but also we deliberately chosen not to do this. And I will tell you why. So let's first talk about normal forms a little bit. So it's, throughout this talk, it's good to understand a little bit about normal forms. So typically in Unicode, there's many characters that you can represent in multiple ways. So for example, if you have an E acute, there is a code point for it, but you can also represent it as an E with an acute sign, modifier. So if you look at the second character, common in Vietnamese, A with a bunch of squiggly stuff. So you have the first, there's also a code point for it, but you can also decompose it into a letter with 2 modifiers. So on the second line, you see the decomposed form, it's normalized, letter with 2 modifiers. On the third line, you see the same character, but the modifiers are in a different order. So this is considered to be not normalized anymore. So in practice, if you're manipulating text, it's very hard to maintain one or the other normalized form. And then also, you don't even know if you will need it in the end, right? So the choice was made to not even do this, right? It's too easy to get a non-normalized string. Even though in practice, right, like most strings will almost always be normalized if you start out with a normalized string, but it's hard to maintain it or give this guarantee. What also turns out is that in practice, there's not that many operations where you really need strings to be normalized. And then doing it on the fly turns actually out to be not very expensive. So you can, so for example, in many of the packages in the Go repo that require normalization, it's done on the fly. So if your string is already normalized, there's no cost. You will not lose any efficiency by having this check. And if it does discover that your string is not normalized, it will normalize just as one segment. And this is very fast, actually. So no random access. So this is a tricky one. It always baffles me why people think this is important. Because basically text processing is inherently not random access. It's inherently sequential. So basically, okay, so you can say we represent everything as UTF-32, for example, and then you have random access, but then what? Because a character can be multiple code points, right? So you're still, you're just raising the problem one level up. So consider this example. So here we have a string with a Korean and an American flag. So these are emojis. It's a relatively new and kind of scary addition to Unicode. Not sure where this is heading. And emojis are typically, in the higher range of Unicode, so 4 bytes in UTF-8. So if I naively want to skip the Korean flag, you would think this would work, right? So what does this print, actually? Well, it prints the Russian flag and an S in a box. So what happens, flags are actually represented by 2 code points, one for every letter in the country code that the flag represents. So, so what happens here if you skip the first emoji, you skip the K, but not the R, so you'll have R and U, which is Russia, and then you have a S in a dotted box left, which is supposed to be the start of a new flag. So what's really disturbing here is that there is no, unlike UTF-16 where you have surrogate pairs, right, and you know which code point is the left and the right one. Actually, it's not a code point, which code unit. Like you have here, with the flags, this is not the case. So if you have an unlimited long string of flags, you have to backtrack all the way to the beginning to actually know which flags you're showing. It's a problem. So this is a little bit of a flippant example, but it just goes to show that text is really inherently sequential, and you have this problem everywhere. Like you have really an infinite number of modifiers that are allowed. So this is valid Unicode. If you have duplicates of them, you just stack them, which is actually used in some languages. Even if you want to take, for example, the title case in Greek, you might have potentially infinite look-ahead in order to determine where you need to upper or lowercase a character, like all these kind of problems, right? It's inherently a sequential problem. So how do you deal with this? So typically, so we're segueing now into examples of the text repo. So typically, like the text packages, you would only use the high-level ones. they will take care of segmentation for you. They will consider characters at the granularity that they need to be considered for that application. But if you want to iterate over characters in a low-level way, this is one way to do it. In the Unicode norm package, there's a function called nextBoundary, or actually it's a method, a nextBoundary in string, and you can use this to iterate over, groups of code points that you consider should be considered in unison. This does not handle emoji because that has its own whole different universe of handling, but it gets you a long way. So let's look a little bit at text transformers. So this is a small grab of the list of text packages or packages in the text repo you saw in the beginning that handle transforming. So what they have in common, all of them, is that the transforms in these packages implement this interface. So this is a very low-level interface. You typically won't need it, but it's sort of good to understand that this is underlying all of it. So the transform interface, you basically take some source bytes, convert them, put them in the destination bytes. You have to specify whether you're at the end of the string or not. This will allow this interface to be used in streaming, converted to a reader and writer and stuff. And then what it returns is how many source bytes were consumed, how many destination bytes were written, and if there is an error. So a typical error would be the destination buffer is full, or there were not enough source bytes to determine, to be able to convert it. This can be if you're not at the end of the string. So why not just use readers and writers, right? So this is the Go idiom, like it's also, basically doing a similar thing. So the thing is that very often, of course, if you're dealing with text, you just want to call a method to convert a string, right? You don't really want to deal with readers and writers and with all the buffers and with all the overhead. But we also don't want to write these functions twice, right? So we basically want to write one function for every kind of transform and then use it everywhere. So this allows us to do that. So the transform functions are also very similar to ICU transforms, which is a special parallel way of handling some conversions. So in ICU, it's a DSL. In Go, it's an interface. So it's actually Go. There's no special domain-specific language. So I looked at a lot of the Google code base, basically at all the uses of the ICU DSL. And basically all the cases that I found were easily covered. Most of them were quite trivial, but even the non-trivial cases were easily covered by the Go transforms. So I think it's a nice model. It also makes it much easier for other people to add to it. So the package transforms provides a bunch of helper functions that let you convert a transform into higher level operations. So like converting strings, bytes, appending, as well as converting into a reader and writer, that kind of stuff. So it's important to know that transformers might have state. About half of them do, I would say. Sometimes it's not really necessary, but it's a performance thing. By having state, you can make it much faster, avoid unnecessary look ahead. And sometimes it's really required. Some of the transforms are quite complex and really require state. Hence the reset methods you saw earlier. So now look at some concrete examples. So if we look at character encoding, so we want to encode a Chinese UTF-8 into the GBK encoding. So we can create an encoder with the top line, and then we can use one of the transform wrappers to basically convert a string from one. If you look at the same, so the same thing below, like one line below, we just basically normalization if you're writing to a file and you want it to be normalized NFC. So you can just wrap any wrapper with this normal form writer, and you're good to go. So here's another example. So this is getting to be more language specific. So this is title casing in Dutch in this case. So maybe you've never even thought about that title casing, upper casing, lower cases can be different in different languages. So this is my native language, so my apologies maybe, but this is a very weird example. So you see the word there, an ijsberg, which means an iceberg. It gets the title cased as follows, as you see in the output. So the apostrophe in Dutch, if it's in a word like this, it's considered to be a letter. So that's the one that gets title case, which is a no-op, really. But the end stays small. And then IJ is considered to be one letter, so they both have to be title cased. So this is also an example where ICU gets it wrong. So basically the formalism that ICU uses cannot handle this. So there's a bug, I filed a bug for it, it's outstanding. They will get to it at some point, but so it's not just that it flows from ICU to Go, it also goes the other way, right? So there's also new features in Go that are making it into ICU, which is kind of a nice side effect. So this also goes to show that, you know, you don't, as a programmer, you don't really want to think about this stuff, right? This just needs to happen. So a low-level example of transforms is the following. So suppose I have a piece of text and I want to remove all accents. So there's a runes package allows you to do, you know, has some functionality to allow you to do transformations on UTF-8. So one of the functions it provides is remove, which creates a transformer that removes all code points out of a set. So the set is really a function that defines if the code point is in it or not. So runes.in allows you to convert a Unicode range table into such a set. So what all this says, all what this does is basically removing all the modifiers from text. So you'd think this would work, right? There's a problem with that. Of course, we have compound characters that have accents on it, and they're considered letters, not modifiers. So how do you solve that? You basically can, what you need to do is to first decompose, right? That would basically tear apart all the letters into their individual letters and modifiers. Then we apply a remove transform, and then just to be nice, we compose it all back together, right? So the transform chain function allows you to do that. It's basically a variadic function that takes an arbitrary number of transformers, and what it returns is a transformer that does exactly that. So you can use this again to create readers or writers. It's fully streaming, and it works just like that. So in practice, if you don't need streaming, it's probably easier to do a bunch of appends in a row, but this is an easier way to do it, I would say. So next topic, language identification. So as I mentioned before, you need to be able to specify to the package like what language you actually want the operations to apply for. So this is a harder problem than you might think. So in Go, we use language tags. So Go uses the BCP47 standard, which is a relatively new standard. So Java is now adopting it too. I think Java and Go were the first. ICU is training a little bit here. So it's a little bit different from what you see in other frameworks where you typically have a locale object that has a lot of data associated with it as well. So language tags here are really only tags, really only identifiers. There's no data. It can be both a locale or a language, however you want to interpret. It's up to the package or whoever uses it to interpret it. So it's pretty agnostic about the interpretation, right? It's just the formalism of defining an identifier. So here are some examples. So the general format is a language identifier, ISO code, which is mandatory, and then an optional script, region, variant to, you know, to basically indicate variations of a language, dialects. And then there's an extension section, which allows you to do more elaborate things if any of these other things doesn't cover it. So some examples. So EN means English. The default is that if it's underspecified, you assume it to be the most frequent one, so in this case, American English. The second one, you have Afrikaans, typically written in Latin, but sometimes written in Arab, mostly in the history, but so that's how you would indicate that. If you want to be specific about the dialect, right, you can say American English by adding the region. Then there are some alternative spellings to English. You can indicate that with variants if they're defined. And also the last one shows you the use of an option or an extension. Here it says, I just want to have regular Dutch, but I want to sort strings in phone book order versus dictionary order. In some languages, this is different. So again, this might seem like a simple problem to you. Like if you say, like, well, I only support like English and German, so it's EN and DE. I just strip off the first two characters, compare it, and if it's the same, I use it. That's it, right? Done. So it's actually not that easy, right? So first of all, there's a lot of aliases and comparable languages. So for example, if you have a Swiss German speaker that requests Swiss German, country code is, or language code is GSW, then it's perfectly fine to return German. A Swiss German will understand German. The other way around is not the case. So it's actually, it's better, you can better serve a German English than if you have a Swiss German web page, for example. It's more likely to be able to read that. So the same thing as the official country code, language code for Mandarin Chinese is CMN, which most people have never heard of. What's more commonly used is ZH. If you're matching languages, you need to understand this, right? So ZH is really the group of Chinese languages. It's a special code for the group of Chinese languages. They're pretty much written the same way, right? Except for being simplified or traditional, but that's indicated in a different way. So as long as you use ZH, it's probably fine, right? Spoken languages, of course, is different. So then in Europe, there's always these fights and political things, and countries decide to split and then all of a sudden decide that they have a different language, even though the language is really the same, but now they have different language codes. So it's kind of, unnecessary. It would be nice if you just mapped the languages, between them, even though it can be a little bit sensitive topic. So for example, like Norwegian is pretty much written in Danish, but if you say that, people might get upset. So you have to be a little bit, careful, but you can always blame the text repo, right, if it makes a mistake. You're not making the mistake. So language matching. So the good news about this is you don't have to worry about this stuff in general, right? So the problem of language matching is really given a set of supported languages that your application supports, and given a set of preferred languages, could be multiple, that the user understands, what's the best match, right? So typically this is a two-step process. So the first thing is to use the language matcher, which is in the language package, to find the best match. And then one of the things it will return is a tag that you can then use in any of the packages to request its services. So here's some code. So all you need to do to define your supported languages is to provide a list to when creating a matcher. In this case, it supports two languages, American English and German. You could also say English. It doesn't really matter. It will ultimately map to the same thing, right? It will behave the same. Only if you start adding both, it will behave differently. And then here's a typical way you would do this in an HTTP handler, right? So there is this header called accept language, where users can specify which languages they understand. So the language package provides a parser for this, and it will return a sorted list of these tags. So all you need to do then subsequently is pass this list of tags to the matcher, to the match method, and you will get your answer, right? So there's multiple return values here. I'm going to focus on the first one first. So that's the one you will be mostly using. So this is the tag. So there's something funky going on with this tag. This is not really something you need to understand. All you need to understand about it is don't try to do anything fancy, just use this tag and don't think about it in any other way. So suppose we're supporting English and simplified Chinese. I indicated the language identifier for this after that. And suppose the user asks Mandarin Chinese, but sorted in stroke order, right? So the core tag will be the same, but the options will be appended. So if you then pass this to collate, everything works, right? Collate will now use stroke sort order instead of pinyin, and you wouldn't even know it, right, that it's doing this under the hood. So one problem is though, so what if you have your own language resources that you want to roll out, right? Now you cannot match the tag returned anymore to the text that you specified to the NewMatcher. So this is where the second return value comes in. So suppose you want to show the flag of the language that was chosen for the user. So again, we have English and simplified Chinese in this case. So two flags, American flag and the Chinese flag. So the second argument that's returned is basically just the index of the language that was chosen, right? So all you need to do is use that index into the flags slice and you get your answer, basically. The third one is the confidence level. So it basically can tell you okay, how certain am I that this is the right match? And it's pretty coarse-grained, unlike other language matchers. So most language matchers use a floating point for it. In Go, it's just exact high, low, or no match, right? There really is no meaning to do anything more than that. So Go uses a very different language matcher than what you have in ICU or even within Google. Google has some pretty advanced language matchers. So I use a more rule-based system instead of like scoring. I don't know why you would use scoring for language matching because the domain is not that big, right? So it tends to be much more exact and it's much easier to manipulate it and add features to it. And there is some, this is also one of these algorithms which is being considered to be backported. So searching and sorting. Again, I mean, this is maybe a little bit more obvious to people that this is a very complicated problem or can be a complicated problem, but you already saw accented letters, right? Strings can be represented in different ways. But there's other problems. Like, for example, in Spanish, CH is considered to be one letter, right? So it has to be sorted as such. In German and Danish, you have sequences of characters that are equivalent to single characters, right? So they're identical. Reordering, like in Danish, they thought it was a good idea to sort A with a ring after the Z instead of after another A, right? It's just convention, right? Difference. So then you have like pragmatic things, like if you have the Kelvin K, it would be nice if you sorted the K, otherwise it's confusing. Like where would you expect people to look for it? Then it gets really funky, like for example, in French, specifically Canadian French. So every single language on this planet sorts in increasing memory order. Even the languages that are written right to left are still stored in increasing memory order from right to left, right? So you always sort in increasing memory order. So in French, it's a little bit different. So you do it for the letters, you do it for the casing, but for accents, you start from the back to the front, right? So if you consider the accents, you look at the last accent first, then you sort it, and then if it's the same, you go back to the front. So the French realized this. It's quite admirable that they did. So they realized it's kind of silly, right? So in the Unicode standard as defined it for French, you don't do this anymore. So they gave it up, right? But the Canadian French are sticking to it. So just for them, right? This needs to be supported, like. Then you get like really, really esoteric stuff like in Tibetan where modifiers can combine into other modifiers that modify letters, and it gets very hairy. So if you want to use the text repo to handle any of this, the biggest problem for you is to know which package to use. So basically there's right now 3 packages you can use. So if you want to search, so for example you have a search string and a bunch of text and you want to find your search string within the text, you use the search package. If you want to sort strings, you will use the collate package. So in some languages, or actually many languages, there is a different sorting order for both as well. A third one is if you don't want to do language-specific compares, but you're more worried about security. So for example, if you're creating a domain name and somebody requests a domain name, you might want to use the secure presses package. I will give you examples of all of these. So then there's other ways to do this. You can use case folding or normalization, for example, to do your comparison. So generally speaking, unless you really know what you're doing, it's probably not what you want. You want to use one of the higher level packages for this. So search and replace. So another common misconception is like, well, my application only handles English, so why would I care about all this complicated stuff? I'm just going to do a byte search and replace. Well, let's suppose I'm writing a blog about being here in Denver and like, okay, I've went to a cafe on the first night and then, well, let's be honest, we went to many, right? So I need to do a search and replace like, a cafe with many cafes. So consider example 1. So this is how most people would write it, I guess. We went to a cafe, so everything works fine. So if you now look at the second example, it won't work, right? Because it's still a proper English spelling. But now we have an accent, so it won't match, which might still be okay, right? But then if we look at the third example where we're now representing this accent as a separate modifier, it will match, but we get this little problem, right? The accent now moves to the S, So you still get incorrect results. So if you want to handle English properly, you still should use the search package and not rely on bytes, search and replace. So to give a little bit more elaborate example, so here in the center we have the text in which we search. In the left column there's the search strings, and on the right column there's the matches. So I use an example for Danish again, just because it's such a fun language for sorting and searching. So here I specify, so Danish, I'm ignoring the case, and I want to ignore diacritics, which is, basically means ignore all the squiggly stuff that you see on characters. And so the first search string, Aarhus, as you maybe remember from an earlier slides, double A matches a ring. We ignore case, so Aarhus matches Aarhus in the text. So Aarhus is, by the way, the city where Dart was developed, but it's also a nice city with a ring in it. So that's the match. So now the second search is maybe a little bit surprising. So I'm searching for A. I say I'm ignoring diacritics, but an A ring is not an A in Danish, so it does not match. It does, however, match the second A, but not just the A, it also matches the modifiers. So really the correct default behavior is to consider all code points that belong to one character and to match that. Right? So that should be at least the default behavior. You might want to override that, but that should be the default behavior. So the third example is also interesting. So this is basically the same character as the one in the text, just the modifiers are in a different order, right? So one of them, I forgot which, is not in the correct, is not normalized. So still the package will match this. Even if you don't specify ignore diacritics, the package will match this, right? So this is unlike ICU, for example, where you have to think about when to use normalization or not. So index string, the return values, they have a start and an end point, right? Because if you're matching a string, it might very well be not the same length, right? So you really have to consider the start and the end point. So for collate, I'll keep it a little bit simpler. So again, to create a collator, you have to specify the language for which you want to collate. You can pass a whole bunch of options. So unt means undefined. That's it's also a language code. So you can use this if you say, okay, I want to sort in a language-specific way, but for any language, right? Sort of the default if I don't know which language it is. So that's a good thing to use. It's equivalent to the same as English, I believe, actually. So all you need to do here is call sort strings on your list of strings, and they will be sorted in the way you might expect, right? So the neat thing about this here, again, you don't have to worry about normalization, but both these packages don't actually use the normalization package, but the normalization data is sort of interwoven into the tables and sort of done automatically. So if you collapse the two problems, the normalization problem becomes much easier. That's why it's also so fast. Anyway, technical detail. So the last thing is secure comparison. So files for various cases like usernames and what have you with others. So for example, you see here two URLs. So they're actually different, right? In the second example, the first C is a Cyrillic S, which looks an awful lot like a C. So basically, you know, this is clearly a security problem, right? So, but you know, with these kind of tools, you can detect this kind of stuff. So last topic, translation insertion. This is the part of the text repo that's most under development, so I'm going to keep it very brief. Probably should be a whole talk by itself. But so the general approach is if you suppose you have your Go application and you have like English texts, user-facing strings, right? The way you localize it is you first have to mark the text that you want to be translated in a certain way, right? Then you typically use a tool to extract that text from your code. You represent it in a certain format, you send that to translators, they will send it back, and then you use the same tool or a different tool to inject it into your code, right? And then, okay, so how do you do that? So suppose we use the format package to basically format this string and print it. So to localize it, all I need to do is to create a message printer, and then instead of calling printf on fumit, call it on this printer. So what I could do, instead of calling it p, I could actually call it fumit, right? And then all the fumit calls in that scope will be, now be localized, basically, or localizable. So, so Ellen and I have been working on this little tool to extract it. We're using all the Oracle and all the fancy Oracle, or now called Guru stuff, right, to do this in a really fancy Go way so we can extract this. It's pretty cool. Upcoming, but not quite there yet. This works, though. This already works. So to insert it back, the code will look something like this. So the original English text will become the key. Doesn't have to be. There's options to override that, but in the common case, you would do that. And then you can provide your translations, just specify the language, and insert it back into the framework. So typically, you won't do that. It's a little bit inefficient with all this code. So more likely, you're going to have a bunch of data and then some init function that inserts it or whatever. But you can program it with this however you want. Right? So in brief, that's translation insertion. So basically, what I've hoped to have shown to you here is basically don't do this at home, right? It's really hard to deal with human languages. There's a lot of like hooks and catches. I've only shown you very few of them. But if you use the package of the text repo, most of this will be handled for you transparently, right? That's the whole point. Q&A.
Any questions, guys? And let's give them a round of applause. That was an awesome talk.